Hey guys, welcome back. In this video, we're going to talk about the relationship between Ka and Kb, right? The equilibrium constant for the acid and the base, all right? And so we're taking an example, HF, and a Ka value for HF is 6.3 times 10 to the negative 4. So as an acid, so we look at this as an acid, all right? Hydrofluoric acid, we put this in water. And on the other side, we get hydronium and fluoride. And remember, every Ka should have this species in the Ka expression, right? So Ka would be concentration of hydronium, concentration of fluoride, all over the concentration of hydrofluoric acid. And of course, it's 6.3 times 10 to the negative 4. Fantastic. If we reverse the reaction, and we do hydronium plus fluoride going to hydrofluoric acid and water. The green K here will be equal to the concentration of HF, hydrofluoric acid, all over hydronium and fluoride, which is the same thing as 1 over Ka. So this is not Kb. All right. Because we have in here, we have our acid for hydrofluoric acid, and we have our conjugate base. And so if you look up the Kb for our conjugate base in the back of the book, you're not going to find it. All right. So for the base of fluoride, from fluoride's point of view as a base, so if you had fluoride and water, what would you get on the other side? Well, fluoride cannot be a proton donor. It's a base. It's got to be a proton acceptor. So we would get HF, and we'd get our hydroxide, which for anytime we have a base, a Kb, this species should be in there. All right. And Kb here would be equal to the concentration of hydrofluoric acid, the concentration of hydroxide, over the concentration of fluoride. All right. How are we going to get this value? Okay. So I'm going to rewrite the Kas and the Kbs here for a second. If I have Ka, and that Ka happens to be the concentration of hydronium, the concentration of fluoride, all over the concentration of hydrofluoric acid. And we're going to have Kb. And Kb's expression is the concentration of hydrofluoric acid, the concentration of hydroxide, all over the concentration of fluoride. And so what is the relationship between Ka and Kb? And some of you might already see, right? Because if we multiply them, what do we get? Well, it looks like I would get the concentration of hydronium multiplied by the concentration of hydroxide. So we get hydronium times hydroxide, right? Because why? Well, fluoride is going to cancel, and hydrofluoric acid is going to cancel. Right? And this happens to be KW, right? So Ka times Kb is Kw. So if we know Ka is 6.3 times 10 to the negative 4th, and we know Kw is 1.0 times 10 to the negative 14th, we can quickly figure out that Kb would be 1.0 times 10 to the negative 14th divided by 6.3 times 10 to the negative 4, which means Kb would be 1.6 times 10 to the negative 11th, which kind of makes sense. So the bigger Ka is, the smaller Kb is going to be, right? Because we know this. So if we go back to the this equilibrium up here with the weak acid, we know that more HF and more water, obviously, water is the liquid, so more HF than more fluoride and hydronium, okay? All right, so Ka is going to be, hydrofluoric acid is a stronger acid than fluoride is a base. But fluoride is still a base. It still affects the pH, all right? So how this works is Ka multiplied by Kb is Kw, all right? And so you'll need to know that going forward, so because in our appendix of whatever textbook you use, right, they'll have acid constants. So HF will have an acid constant. Ammonia will have a base constant. So there'll be KBs back there too, but they'll only offer one. So they'll offer HF, but they will not offer fluoride. They'll offer ammonia as a KB, but they won't offer ammonium as a Ka, but it has one. All right? And so that's very important. So this is very important. Ka times Kb is Kw. And that's the relationship between Ka and Kb. All right? I hope that helps. And we will see you in the next one, guys. Take care.